In this video, we will work through some multiple choice questions from past AP Calculus exams, which pertain to first semester. In first semester, we learned about limits, derivative rules, and applications of derivatives. Problem number 1. At what value of x does the graph of y equals 1 over x squared minus 1 over x cubed have a point of inflection? Remember that a point of inflection is where a function changes concavity. For example, if a function changes from concave up to concave down, that will be at a point of inflection. A long time ago, we learned the graphical relationship between f, f prime, and f double prime. The part that's relevant to this problem is that we know a function will be concave up when the second derivative is positive, and concave down when the second derivative is negative. Therefore, the function will change concavity if f double prime changes signs. So our strategy will be to find the second derivative and then investigate where it changes signs. So let's rewrite this a little bit before we get started. 1 over x squared is the same thing as x to the negative 2 power, and 1 over x cubed is x to the negative 3 power. This will make it easier to apply the power rule. So let's take the first derivative, y prime. Using the power rule, we have negative 2x to the negative 3 power. Negative 3 times negative 1 is positive 3, so I have positive 3x to the negative 4 power. So there's your first derivative. How about the second derivative, y double prime? We'll do the power rule again. Negative 3 times negative 2 is positive 6. Positive 6x to the negative 4 power. Negative 4 times 3 is negative 12. Minus 12x to the negative 5 power. So this is the second derivative. I need to go ahead and rewrite this with positive exponents as I prepare to figure out where the sign changes are. So this will be 6 over x to the 4th power minus 12 over x to the 5th power. In order to find where y double prime changes signs, it will be useful to write this as a single fraction. So I need like denominators. If I multiply it by x over x, I will have like denominators. Both denominators are now x to the 5th power. So this means that y double prime is equal to 6x minus 12 over x to the 5th power. Y double prime can only change signs where y double prime is equal to 0 or where it is undefined. So, where is y double prime equal to 0 and where is y double prime undefined? Y double prime is this fraction right here. A fraction will only equal 0 when the numerator is equal to 0. So the second derivative will equal 0 when 6x minus 12 is equal to 0. Adding 12 to both sides and dividing by 6 gives me x is equal to 2. So this is one possible location of a sign change. Let's keep going. Where is y double prime undefined? Well, this fraction will be undefined wherever the denominator is equal to 0. But this means that x itself will equal 0. So this is another possible location of a sign change. We will figure out whether or not f double prime changes signs by making a sign chart. So I'm going to set up a number line and I'm going to put these values on it and we'll investigate from there. So here are the two critical values on this number line. Make sure you label your sign chart as F double prime. And let's see, how many rows do we need on this sign chart? We're going to need one row for the numerator and another row for the denominator. So those are the only factors that we have. Next, we need to figure out whether these factors are positive or negative in each interval. So at x equals 2, this first factor is equal to 0. 6 times 2 is 12, minus 12 is 0. If x is anything less than 2, I'm going to get a negative value. So, for example, imagine that x was 1. This would be 6 minus 12, that's a negative number. If x is anything bigger than 2, I'm going to get a positive number. Of course, looking at x to the 5th power, if I put in a positive number, I'm going to get a positive result. So anything bigger than 0 will be positive. Anything less than 0 will be negative. But what about the overall sign of f double prime? In this first interval, we would have a negative divided by a negative. That would be a positive. In the middle interval, this is a negative divided by a positive, which is a negative. And in the final interval, we have a positive divided by a positive, which is a positive. So before I look to see where the sign changes are, we need to pay attention to whether or not either of these values are undefined for the original function, because you can't have a point of inflection if it's undefined. So if you look back at the original problem, okay, this is the original function y. X cannot be 0, right? Because you can't have 0 in the denominator. So I can forget about a 0 as a possible point of inflection because the function is not even defined at 0. So even though I do see a sign change right here, that's not a point of inflection. However, notice that f double prime goes from negative to positive at x equals 2. So there's your point of inflection. If this were a free response question, I would record my answer and justification like this. F of x has a point of inflection at x equals 2 because f double prime changes signs. However, this was a multiple choice question, so the answer is C. Problem number 2. What is the limit as x approaches 0 of this expression? Let's see what would happen if we tried to do direct substitution. If I let x equal 0, then I have e to the 0 power. And e to the 0 power is 1, then we have 1 minus 1, which is 0. So the numerator here would be 0. What if I let x be 0 in the denominator? Well, the tangent of 0 is also 0. We have learned that if direct substitution gives you 0 over 0, we are allowed to use something called L'Hopital's rule, which says that we can take the derivative of the numerator and the derivative of the denominator without changing the limit. So let's give that a shot. Taking the derivative of the numerator term by term, we first do the derivative of e to the 2x power. Taking the derivative of e is always fun because the derivative of e to the something is always still e to the something. If this is just x, I would be done. But because I have a function inside of a function, I need to use the chain rule and multiply by the derivative of this inner function. The derivative of 2x is 2, so I need to have that. The derivative of a constant is 0, so we're done. We've taken the derivative of the numerator. I think I'll put the 2 in front just for fun. We have memorized that the derivative of tangent is secant squared. So let's see what happens if we do direct substitution now. The 2 times x becomes 2 times 0, so this is e to the 0 power. Let me just go ahead and show this, I guess. So we'll have 2 e to the 2 times 0 power over secant squared 0. So this is e to the 0 power, which is 1, and 2 times 1 is 2. So what is secant of 0? Okay, off to the side, I'm going to work this out. Secant is the reciprocal of cosine. So I'm going to first ask myself, what is the cosine of 0? And on the unit circle, 0 is right here. The coordinates are 1, 0. Cosine is the x value. So cosine of 0 is 1. Secant is the reciprocal of cosine, so secant of 0 is also 1. If we square that, that's secant squared will be 1 squared, which is still 1. So we end up with 2 over 1, which is 2. So the answer is D. Number 3, for which pair of functions f of x and g of x below will the limit as x approaches infinity of f of x over g of x equal 0? Let's just try them out one by one. Before we go any further, remember that the acronym FEPL reminds us that as x approaches infinity, some expressions grow faster than others. Specifically, FEPL ranks the various types of functions in order from fastest growing to slowest growing. So looking at the expression that is first, e to the x power over x squared, we see that we have an exponential expression in the numerator. And then we have a polynomial expression in the denominator. However, according to FEPL, exponential expressions grow faster than polynomials. So even though the numerator and the denominator are both approaching infinity, because the numerator is growing faster than the numerator is getting bigger and bigger compared to the denominator. So therefore, the value of the fraction overall is getting bigger and bigger and bigger. So the value is approaching infinity. So in general, we would say that the limit does not exist. But certainly the limit is not 0. What about the next pair of functions, e to the x over natural log x? Well, the numerator is still this exponential function. The denominator is logarithmic. So we've got exponential versus logarithmic. Exponential is still growing faster. That is the same as before, and the limit is still approaching infinity, or does not exist. For the next pair of functions, we have natural log x over e to the x. So we have a logarithmic expression divided by an exponential expression. So the logarithmic expression is growing slower than the exponential. If the denominator is growing faster than the numerator as x approaches infinity, then the denominator is getting bigger and bigger compared to the numerator. In that case, the overall value of the fraction is getting closer and closer to 0. In other words, the limit is 0, and C is the answer. Number 4, let's find the limit as x approaches 0 of this function. First, let's see what would happen if we did direct substitution. At first, we get this, but we know that sine of 0 is 0, the cosine of 0 is 1, and sine of 0 again is 0. 0 squared is 0. So obviously in the numerator we have 0, and in the denominator we have 0. Because the numerator and denominator are both approaching 0, we are allowed to use L'Hopital's rule, which says that we can take the derivative of the numerator and denominator without changing the limit. Let's take the derivative of the numerator term by term. For the sine times cosine term, we're going to use the product rule. So we have the sine x and we have the cosine x. The first time through, we take the derivative of sine, which is cosine. And we leave the cosine alone. And we put a plus. Then we pass through again. The second time through, we leave the yellow function alone. And we take the derivative of the blue function. The derivative of cosine is negative sine. So I'm going to put sine x here, but because this is negative sine, I'm going to change this plus to a minus. So we have this. So that's it for the first term. We still have to take the derivative of sine x, which is cosine x. Let me scroll over a tiny bit. So we will have minus cosine x. And in the denominator, the derivative is 2x, just using the power rule. We can simplify this a tiny bit by writing cosine as cosine squared and sine times sine as sine squared. Let's see what would happen if we did direct substitution now. At first, we have this. But we know that cosine of 0 is 1, so we would have 1. Sine of 0 is 0, so that's 1 minus 0. Cosine of 0 is 1, so that's minus 1. 2 times 0 is 0. 1 minus 1 is 0, so we are still getting 0 over 0. Because the numerator and denominator are still approaching 0, we can use L'Hopital's rule again. So let's again take the derivative of the numerator and denominator and see what happens. First, I take the derivative of cosine squared. I'm using the chain rule. So the derivative of the outer function is 2 cosine x. But now I have to multiply by the derivative of the inner function. The derivative of cosine is negative sine. So I'm going to put sine x, and I will put the negative sign in the front. Similarly, when I take the derivative of negative sine squared x, the derivative of the outer function puts the 2 in the front, so I have minus 2 sine x. And then the derivative of the inner function, the derivative of sine x is cosine, so I have to multiply by cosine x. That brings me to the third term. The derivative of cosine is negative sine. So I'm going to put down sine x. But because it is negative sine, it's going to change the negative to a positive. So I will end up with plus sine x. The derivative of 2x is just 2. If I do direct substitution now, I get negative 2. Cosine of 0 is 1. So I'm going to just go ahead and put 1. Sine of 0 is 0. And I've got minus 2. Sine of 0 is 0. Cosine of 0 is 1. Plus sine of 0 is 0. So that's my numerator. In the denominator, I just have 2. Well, every term has a 0 in it. So that means that the numerator is going to be 0. So I have 0 over 2, which equals 0. So the answer is D. In order to do problem number 5, I need to remind you that this is the traditional definition of the derivative f prime at c. You really want to memorize this. So if you see a limit that sort of reminds you of this traditional definition, write it down and then compare. So I think the best place to study it is right here. Compare f at c to tangent of pi over 6. So when you look at those two yellow parts, you can see that the function f must be the tangent function. So let me write that down. F of x is the tangent of x. And then when you notice that inside of the tangent is the pi over 6, just like inside of f at c is c. So that tells us that the c must be pi over 6. And if you kind of look at the rest of it with the pi over 6 plus h, so that would be the c plus h, everything matches f prime at c, the definition of this derivative. So in other words, this entire expression is just another way of writing f prime at c. Therefore, to evaluate this limit, the easiest thing to do is to evaluate f prime at c, where this is f and this is c. So what is f prime? Well, if function f is tangent, then f prime will be secant squared. We've memorized that the derivative of tangent is secant squared. But we want f prime at c. And c is pi over 6. So that means, that means secant squared at pi over 6. So all we need to do is evaluate this, and that'll be the answer. So here's my thought process that I would do all of this in my head. Secant is the reciprocal of cosine. So first of all, what is the cosine of pi over 6? That is radical 3 over 2. Well, in that case, secant of pi over 6 should be the reciprocal of this, which will be 2 over radical 3. Then what about secant squared? I'll go ahead and put that down. If I square this, that's going to be 4 over, and if I square radical 3, that's just 3. So f prime at c, in this particular case, should be 4 over 3. That means the answer is B. Number 6 is the same type of problem, so I'm going to do this more quickly. Look at the last term in the numerator. This is going to tell us the f of x, and it will tell us the c value. And eventually we will be evaluating f prime at c. But f of x must be 5x to the 4th power. So f of x must be 5x to the 4th power. And c must be 1/2, since that is what is being plugged in. So c is 1/2. So let's begin to evaluate f prime at c. So f prime, first I'm going to just do f prime at x. The power rule, so 4 times 5 is 20, so 20x to the 3rd power, that's f prime. Now, how about f prime at 1/2? So that would be 20 times 1/2 cubed. So just evaluating, I have 20. 1 cubed is still 1. 2 cubed is 8. So I have 1/8. This would be the same as 20 divided by 8, and this will reduce down. All right, dividing each of these by 4, that's going to be 5/2. So that should be the limit. So the answer is A.